Example 4.2.2b, three-phase transformer calculations. A three-phase transformer bank is designed to handle 500 kVA and have a voltage ratio of 34.5 kV to 11 kV. Find the following ratings for each of the individual transformers used to construct the bank. We want to know the high voltage rating of the transformer, the low voltage rating required of the transformer, the turns ratio between the high voltage and low voltage side, and then what is the apparent power rating required of each of the individual transformers used if it's in any of the standard three-phase transformer configurations, YY, delta delta, Y delta, and delta Y. And what this example is going to illustrate is how each of the different three-phase configurations is going to require a slightly different transformer to implement it because of the difference between the two three-phase connection types. So what we were given from the problem statement is, first we were told that the bank needs to handle 500 kVA. Remember, that's a three-phase rating, so the three-phase apparent power is 500 kVA, and it wants to have a voltage ratio of 34.5 to 11. The bank wants that. So what that's saying is that the line-to-line voltage on the primary side needs to be 34.5 kV. That's the primary rating here. And the line-to-line voltage on the secondary side, the output voltage on the secondary side, should be 11 kV if the input voltage is 34.5 kV. So we can interpret those as that's the input rating on a line-to-line basis, and that's the output rating on a line-to-line basis. So what we want to do with that information is find the following. What is the single phase apparent power rating required of the transformers we're going to use? You know, we're going to be using 3 different transformers. How much apparent power does each of them need to be rated for? And of course, we want to know what the line to neutral rating on the primary is. What's the individual transformer need to be rated on the primary, line to neutral? Of course, we want to know what the line to neutral rating on the secondary is. And then for each of these, to get this particular voltage ratio, we need to know what NP over NS is. And I'll remind you, sometimes we call that A. So that summarizes what was given to us in the problem statement, and we'll begin the solution next. And all of these solution methods are going to involve the same power calculation. I've got 500 kV total three-phase power that needs to get delivered, and it doesn't matter how the transformers are configured. Each of the transformers is just going to deliver a third of that in a balanced system. So S1 phase, no matter the transformer configuration, is going to be S3 phase over 3, assuming balanced system operation. So that's 500 kVA divided by 3. And so that gives us approximately 167.0 kVA for all of the connections. Doesn't matter if it's delta delta, YY, Y delta, or delta Y. Each of the individual transformers used to build this bank needs to be rated to deliver 167 kVA. So we don't have to repeat that calculation for each of the different configurations. So that's for all of them. So now I'm going to go through A through D and find out the different voltage and turns ratio calculations that are being asked. So first we'll start with the Y connection. And so I always find it helpful to go ahead and draw the connection. So there's a Y transformer on the primary side, and there's the Y transformer on the secondary side. And remember, what we were given was the line to neutral quantities on the primary and secondary. And so line to neutral, or sorry, we were given line to line quantities. That's how three-phase transformers are rated, are on a line to line quantity. So this was 34.5 kV, and here to here was 11 kV. So if I want to know, if I'm given a line to line quantity in a y and I want to know a line to neutral quantity, I just use the relationship that v line to line is equal to, or the magnitude of it is equal to √3 times the magnitude of the line to neutral quantity. And this is the one I'm solving here, so I want to rearrange that equation to say that v line to neutral is going to be equal to v, not L, v line to line divided by the square root of 3. So we'll just do that calculation twice, once for the primary side and once for the secondary side, since both of them are configured in y. So what we're going to find is the magnitude of the line to neutral voltage on the primary is just going to be 34.5 kV divided by the square root of 3. And that gives us about 19.92 kV. I've rounded that a little bit. And then the line to neutral on the secondary is just going to be 11 kV over the square root of 3, which gives us 6.35 kV. So the turns ratio of each of the individual transformers, of course, is based on the line to neutral quantities. So NP over NS, that required turns ratio to get this three-phase output voltage of 34.5 kV to 11 kV. We need to use the line to neutral quantities to determine that, and that's going to be 19.92 kV over 6.35 kV equals 3.14 for our turns ratio necessary in the Y to Y. So we're going to move on to the next circuit, the delta circuit. And so I will again start by sketching that. So both the primary and the secondary of the transformer are arranged in a delta configuration. So that's what that looks like. And again, we are given the same line to neutral ratings, or sorry, line to line ratings. That's here on the primary at 34.5 kV, and that's here on the secondary at 11 kV. So this is a delta system, so the magnitude of the line-to-line voltage is actually equal to the magnitude of the line-to-neutral voltage. The line-to-line voltage appears over a single phase, and so we can very easily calculate the magnitude of the line-to-neutral rating for the primary. That's just 34.5 kV. And the magnitude of the line to neutral on the secondary is just going to be 11 kV. So the turns ratio required if I'm in a delta-delta, again, is going to be the phase quantities, which are 34.5 kV over 11 kV. And that's going to give us a value of 3.14 turns ratio. So interesting that it doesn't matter what the turns ratio is in a Y system versus a delta system. They're the same. What is different is the individual voltage ratings. We see that the delta transformer, individual transformers need to have a much higher voltage rating than they do for the Y system there. Okay, so we're going to move on to the first of the Y delta configurations, and that's with the Y on the primary and the delta on the secondary. And so what that's going to look like is that right there on the primary. And on the secondary, we're going to have this configuration right there. So Y delta. And we just want to mark out again what the line-to-line quantities are. So for a Y, the line-to-line goes across two phases. That's 34.5 kV. And in the delta system, the line-to-line quantity is the same as a phase quantity. It's right there. So that's 11 kV. So we have two different formulas this time. For the primary side, we know that the magnitude of the line-to-line on the primary is going to be equal to √3 times the magnitude of the line to neutral. right? Line to line is always root 3 times line to neutral in a Y system. And so we can say that the magnitude of the line to neutral voltage on, oh, I should have put primary over there. On the primary side is just going to be 34.5 kV divided by the square root of 3. And we know that now to be 19.92 kV. And for the delta system, the phase voltage is the same as the line-to-line voltage. So for the delta, we've got the magnitude of the line to neutral on the secondary is just equal to the magnitude of the line to line on the secondary. So that's just going to be equal to 11 kV. The turns ratio then is going to be 19.92, the phase quantity on the primary, divided by the phase quantity on the secondary. So that's 19.92 divided by 11 kV. So we need a much smaller turns ratio for the Y delta system of 1.81 as compared to 3.14 there. The final three-phase configuration for a transformer that we can have is the delta Y. Sorry about that. Don't know where that came from. The delta Y. And so we've got a delta on the primary, and we have a Y on the secondary, and we just mark our given rated voltage on each, not 3.45, 34.5 kV. And over here, of course, we have 11 kV line to line. So on the primary, voltage line to line on the primary, its magnitude is equal to the voltage line to neutral on the primary. So that's going to be equal to 34.5 kV. And then for the secondary, the magnitude of the line to line voltage on the secondary is root 3 magnitude of the line to neutral voltage on the secondary, since that's a Y configuration. So that means the line to neutral quantity over here on the secondary is going to be equal to 11 over root 3. That gives me 6.35 kV. So to create a delta Y with a overall three-phase voltage ratio of 34.5 to 11. My individual transformers need to be rated at 34.5 on the primary and 6.35 on the secondary, both in kilovolts. That means this transformer for the delta Y needs to have a turns ratio of 34.5 kV over 6.35 kV, which is 5.43. So a much higher turns ratio for the delta Y system than we observed in the others. So hopefully this gives you some sense about if we're creating an overall similar three-phase system where we want 34.5 kV line to line on the input and 11 kV on the output there, how we'll have to choose different individual transformers depending on which one of the configurations our system is using. They all do have very different voltage and turns ratio requirements. However, they do all have the same power requirement. Every one of those individual single-phase transformers that we are speccing needs to be rated to 167 kVA. It doesn't matter if it's a YY, Y delta, delta Y, or etc.